Hey class, today we're testing out a new drawing tool, Paint 2, so hopefully this goes well. Okay, so first we'll start off with the review of gravitational potential energy, which we know looks like this. A U, which represents potential energy, and it's denoted by a G, which means it's a gravitational potential. And we can picture gravitational potential energy as the amount of energy an object has available to do work as a result of being located at a particular position in a gravitational field. And we can picture this as perhaps Earth's gravitational field. So when we have a big old Earth, something like this, and the center of mass of that Earth, then here an object can be located at a distance r from the center of mass, and we can think about that like this. So most of the objects we're going to be talking about are going to be located at some surface on the Earth. So we can say UG is the force of gravity in the case of objects on the Earth. And this is the force of gravity at some distance r. So we can say that UG on Earth is equal to the force of gravity times some distance r, or perhaps you can call it h2 as well. So in this case, h and r are the same thing. Most commonly, we can express the whole thing as this. Let's get rid of these. And now, we can we're most likely to see things expressed in the form of mgh, where fg is mg. Okay, so now we can think about this stuff as if there was a sort of reference point for us to work with. And usually we pick the surface of the Earth as the reference point. And so our picture of how we calculate gravitational potential and potential energy of an object changes from an image of Earth as a whole to just the surface. So think of this as the surface of the Earth, where everything else is down here. And then we can say that we have some kind of mass m above the surface of the Earth at some height h. Now, in order to be able to predict the motion of an object, we have to apply the idea of gravitational potential energy as something that can be used to produce a force and velocity. This requires a transfer of potential energy into kinetic energy. And now we can see the relationship between potential energy and kinetic in our conservation of energy equation, which we've seen before. It looks like something like this. Energy total of a system is equal to potential energy plus the kinetic energy, K. And so we can transfer both of these concepts and break them down into, in this case, mgh. And then T is going to be equal to 1/2 mv squared. So in this case, it's clear that we can see how some kind of change in height in some gravitational field can be related to a velocity. of that object in the gravitational field. Now we see this transfer of potential energy into kinetic all the time. You can hold our hands out with an item in our hands and drop it to the floor. That was my physics textbook hitting the ground. And so that really represents how we transfer and convert different forms of energy all the time, every day. And now we're going to use these concepts to really try to describe the motion of an object. We can do this through an example like something like a pulley system. So here we'll set up the scene. We'll have some kind of ceiling, some kind of surface. We can say the earth. Label that E. And let's see, we have a pulley system here. Say that's the pulley system. And a rope holding a mass some distance over the surface of the earth. And we'll have somebody holding that. Let's say they're on a box. Okay. So here we can go back to our concepts of potential energy. And label this H. And so the person here is essentially holding the mass a height h above the ground. In this case, there is a buildup of potential energy in the object. Let's say the object is 25 kilograms. So our mass is 25 kilograms. And let's say h is a height of 10 meters above the ground. So we can calculate our potential energy to be, to UG equals mgh. So that's going to be 25 times 10. Let's go back actually on that and put our gravitational potential in first. So G is going to be our acceleration due to the gravitational field of the Earth, and we know G to always be 9.8. And now we can multiply by the height of the object, which is 10. So U is going to be 2,450 joules. So now, how fast will this object be right before it hits the ground? Now we can use this concept of energy total. To predict what will be the kinetic energy. So when this object has just about hit the ground, it will be going at a certain velocity. At this moment in time, the potential energy will have changed, and h will be essentially 0. So here we can say h equals 0. Now if h is equal to 0, then so must u. Now, looking at our equation over here, energy total in a system is always constant, so if U, potential energy due to gravity, is 0, then T must have taken up all that energy. So then we can say that T, kinetic energy, must be now be equal to 2,450 joules. And if we look at how we describe kinetic energy, we see that it is equal to 1/2 mv squared. So now it becomes a simple algebra problem to figure out what the actual velocity in this case is. So I'm going to let you do that and take a moment and pause and figure out what our velocity is going to be.